Welcome, everyone. This is intended to be a 60-minute session, may go a little over, but hopefully you would take away a lot of things and enjoy this journey that I have to share. So yes, a little something about myself. Just one line: I'm a guy who likes to solve problems. Everything else is secondary. I think most of the attendees or people who would watch this would also be of the same kind, who like to solve problems. Yes, why am I at an advantage? I mean, apart from my experience, again, first principles, computer science, software engineering, data engineer, big data, data science, understanding of product and business and marketing, a little bit of everything. So kind of a potpourri of everything. And I really like DataHour. I myself have used Analytics Vidya's resources. I do a Google search. I find, resources coming from Analytics Vidya. So strongly encourage. I saw Varun Behel's video on DataHour on statistics in a broad overview. It was really good. Debanjan Sarkar's thing was also really nice. There's a very cute little video on decision tree and entropy and C4.5 or C5.0 by Analytics Vidya. Encourage you to click on this link and see it. And then in the past, how to handle imbalanced data set with SMOT and all those techniques. These were also things that I found via Google search at Analytics Vidya. So your takeaway in the next 60 to 80 minutes, techniques used to solve different problems via use cases. You should be able to back up your claims with quantification, which is a very important thing when you present your data science case studies and when you find something and you justify the existence of your study in a real-time system or even as a post-facto analysis. You'll realize how statistics and analytics are used for policy making. This may really surprise you for folks who know Poisson process or binomial distribution. You'll see how it was used very simply by me and my team. And I was really fortunate to work with some really smart folks and also apply them and make them practical reality in many companies. Another takeaway is you start with fast and approximate before trying to go, full Monty, before getting the best result. And that's that, iterative process, even in your deployments, even in your process of understanding data is very crucial. It's better to make small progress than none at all trying to make it all the way through. Being creative with data. As you can see from my background, there are some paintings and artists create wonderful things. Try to be an artist with data. Try to understand the math. Don't get flustered. Many of the students here do invest your time in trying to take courses that will advance your understanding, and you need to be at it. You may not understand it the first time. So be creative with data and learn to use formulae and natural processes to your advantage. And I've got some resources at the end, some online courses, some books, some videos and blogs. You may find this really interesting. And if you have more, I request you to share it, in the comments of the YouTube video as well, or share it with the DataHour team at Analytics Vidya. So I'm going to talk about 6 use cases. It's really hard to capture 6 use cases in 1 hour because there is a whole background of the problem that needs to be explained. But I'll try my best. And if there's any one thing that you find interesting, you can always go back to DataHour and ask them to schedule where I'll do a double click and deep dive into each of these use cases. I'll try to explain the problem as best as possible and with sufficient depth that you can take it on by yourself, or you'll at least gain something by yourself. All right. So the first use case, and I'll do a quick check on time, 8 minutes up. Okay. The first use case, distance calculation for mobile taxi. I'll stop sharing my screen and explain a little more visually after the next slide. Basically, when you are, today, of course, you have mobile taxi all over. You have Careem in the Middle East, you have Uber and Ola in India. You have Uber all over the world, actually, and many other companies, right? Lyft and so on. So the evolution of this thing where a meter, if you're old enough to know that there used to be a meter in a taxi or a transportation vehicle, and then you would pay based on the meter, and the meter would compute the amount based on the distance traveled and the time taken. So if you're stuck in traffic, also the driver's losing revenue. So it's kind of a function of both time and the distance. So that was replaced. The meter was replaced by the mobile device and a server at the back end. So when you went on a trip, a taxi driver's device app sends location, geolocation every few seconds to the server. Devices from different manufacturers, and things have gotten much better now, but there was a time when there was a lot of discrepancy. The GPS was not trustable. If you were in a forest or a thicket covered by trees, your GPS location would be off very often. And at one point in time, we had noticed that about 4% of the times, the GPS location was really off, maybe 100 meters, maybe even 100 kilometers off. There are stories of all this kind that was happening. Typically, what happens is when the trip ends, the driver device contacts the server and tries to get the amount for the trip. But there are times where you stop, the taxi stops at a location where there is no signal, and the passenger has to leave, and you need to get a transaction going. So at that point in time, the device that the driver has needs to do the computation without having to go on the air and make a calculation. So the problem was, you're a software engineer or a product manager in a taxi cab company. There are lots of complaints that distance measured for a cab ride is wrong and is inaccurate 20% of the times. The support calls are increasing. Riders and drivers are both unhappy. Your brand is affected badly. You're busy issuing refunds to retain customers. And you as an engineer or a product manager or a data scientist have to fix the problem and analyze and really come up with something that's consistent and long lasting, right? So what I cannot capture on a slide or even in a presentation is the commotion. Everyone had opinions, right? Right from the CXOs, right down to the engineer or the QA engineer or the data scientist or the product manager, everyone had an opinion. There was a lot of pressure and desperation and frustration that we were getting so many support calls, and we were burning money pretty fast of the investors by issuing refunds. No one had a clue how to solve it. So take a step back, take a deep breath, try to solve it. No one had. People were trying for quick fixes. Each one was trashing the other solution, with conjecture. So it was not backed with data. Site leads were making fun on WhatsApp groups that we have a cab in the middle of the ocean. It was getting frustrating for engineers to read such things, engineering leadership to read such things. But the fact was that there were problems in the device calculation for and the device GPS location. Just to give you an idea as to how this would have panned out, let's say that X is the reported lat long of the geolocations of a taxi ride, whereas the green line was the actual trip, right? Obviously, the length of the red line will not match the length of the green line. And this is just a made-up example. But if you take a long trip, say even 3 or 4 kilometers, or even at least 3 or 4 kilometers, or even more than 1.5 kilometers, you would see that there's discrepancy, and the passenger would get surprised. Hey, this is exactly 1 kilometer. Why are you charging me for 1 kilometer and 1.2 kilometers? Questions of that sort. So an analysis was done with the data team, the engineers, and the QA and the black box testers. And it was found that cheaper devices give incorrect geolocations up to 4% of the times. While waiting in a traffic signal, the points are returned 50 meters away, and say you're waiting in a traffic signal for about a minute, your consecutive points are, scattered all over the place, and they add up to the distance. Geolocations of some devices had an offset of a few meters away from the road, always consistently to the right. And 30% of the taxi drivers were using cheaper devices because at that time we had a bring your own device to get onboarded as a driver on the platform. And rupees 3,000 is really, really cheap for a smartphone. And even back then it was pretty cheap. Of course, back then even now even more so, but back then too it was pretty cheap. So yes, this was the analysis done. So I'll go to the fix. I know I'm cutting short a lot of the things that happened, but hopefully you'll get some learning from this. This is not the greatest of use cases, but it's still a use case that solved a company pain point. So we reduced the sampling from 1 GPS location per second to 1 GPS location every 5 seconds. Now, we didn't need that level of accuracy of going every second. 5 seconds seemed to be fine. Now, assuming that the maximum speed that the driver does is 150 kilometers per hour, we removed outlier points greater than 150 kilometers per hour. So if I am a particular point, and the next point, and I know if that the particular point is correct, because historically also it seems consistent, but the new point comes at 150 kilometers speed for 5 seconds, so whatever that distance is. If that point comes beyond 150 kmph times 5 seconds, we would then drop that point completely. And then we use simple moving averages for consecutive points after dropping, outlier points. And we got actually very good results. So here's an example which I made on Google Sheets. You have the latitude and the longitude. And as you can see in the red here, suddenly one point is like 933 or 933,000 meters away from the earlier point, right? And then the GPS corrects itself to get back again, back to the 77 latitude, longitude. Now, these kind of points need to be like eliminated, right? And obviously, if you were a taxi cab company and you said that the distance traveled was the size of the equator, the length of the equator, then people are going to make fun of you and you're going to hurt your brand pretty bad. So with this kind of analysis, which is automatable, we removed outliers, and this distance calculations, by the way, done using haversine distance, which is commonly used. And then if you look at the histogram, the about 1,000 distance, is easily something that can be removed. And after removing that, if you see the distance without moving average, we got about 1,161 meters. But then if you know the working of the points, they come on either side of the main road. If you take a 3-point moving average, you get 954, which seems more in line with reality. Yes, it may be off, but the point is, why do you choose consistency over, why do you choose accuracy over consistency? You're fairly accurate, but you are more consistent this way. So the outcome was that tickets dropped from 20% to 2%. The learning was choose consistency over extreme accuracy wherever possible. And everyone has learned simple moving average, but rarely does it strike somebody where to apply it. This comes with experience. Again, not the best data science example you may have, but the impact of this solution was tremendous, and everyone was silent and happy and went back to work and added new features and so on. So this is my first. It's taken me 10 minutes to explain this first use case, and I will quickly move on to the next one, which is connivance between driver and customer, fraudulent connivance. I'll stop sharing my screen so that you can see my video. So here is a situation where we knew there was fraud. we had enough statistical evidence that there were taxi drivers doing too many trips within 12 hours of duty, or there were taxi drivers who were doing too many short trips compared to the rest. You always do a comparison, right? So you have a bell curve, you have the left tail, you have the right tail, and these are your starting outliers and so on. It is very important to catch all kinds of frauds and penalize those fraudsters, either by banning them from your system or filing a case against them in the police, for the simple reason that it sends a clear message that you are interested in making a good marketplace, and you're interested in doing business. This one technique blew my mind, and hats off to my friend Abhishek, who came up with this. Abhishek was at that time, of course, a really smart guy, an engineer and a management from Indian Institute of Management, a really sharp guy. He was not a software engineer. And the concept of data science had just started back then, or was still nascent. And the technique this guy used, it blew my mind, and it blew everyone's mind around us. So I'm going to go back and share my screen on the use case. So whenever a marketplace platform incentivizes supply side, you should expect fraud. Sometimes the seller masquerades as the buyer, or many sellers connive becoming buyers for each other. There are many indicators of fraud, but you don't have solid evidence. Again, this context, the first example is a context in Bangalore. Can a driver go from Koramangala to Indiranagar in 5 minutes in the daytime on a weekday, or from Gurgaon to Noida in New Delhi in 7 minutes? Impossible, right? But you see these kind of things happening, and these are like sure shot cases of fraud. Now, you will have to write a lot of queries to make sure that you catch a lot of these frauds, and you'll have to create some sort of a system that monitors for these kind of frauds. When the average driver does 8 trips in 6 hours, how could a driver, or any driver for that matter, do 12 trips in 4 hours? Now, how can a city that had 2,000 trips a day have a linear increase to 22,000 trips per day in 2 weeks? Something's happening, right? It's beyond your imagination, or it's the unexpected. And statistics effectively does catch the unexpected. So, but that's not enough. It's not enough to be to just catch the unexpected, because you're only catching those thieves who have done excessive robbery, not the ones who've done a little bit or keep doing consistently a little bit regularly. So now imagine a matrix where you have drivers as your rows, and as columns, you have the customers. And for simplicity's sake, I'm not putting numbers that are greater. I'm just keeping 1 and 0, 1 and nothing. 1 is that the driver has worked with the customer. So in this first case, D1, C4, is that this driver has worked with customer 4. This driver has worked with customer 6. This driver has worked with customer 8. So this is basically what the matrix is to begin with. From this, can we get a cluster or set of clusters where there could be connivance? Okay, where there could be connivance between driver and customer. This clustering technique is known as bi-clustering, and it's got a simpler form called rank order clustering. You should see that video of rank order clustering. It's in a different domain, in the industrial engineering domain, but it's so cute and so simple that it'll help you understand bi-clustering. And bi-clustering is implemented using bipartite spectral clustering. I know these names are big, but trust me, once you understand them, then these names get internalized. This is used in so many industries, industrial engineering to genetics, right? Even biotech uses bi-clustering quite a bit. And even for diagnosis of patients, right? People with some kind of blood deficiencies have, so imagine, so drivers and customers, you have diseases and conditions of people. diabetes, blood conditions, deficiencies, and so on. So you'll kind of get those clusters where conditions and diseases kind of match. Um, and then hats off to my buddy Abhishek. He's quite reticent. He doesn't like to be publicized too much, and I had to take his permission to take his name. But he identified this technique, the application of this technique into the problem space. And you should check out this video by Professor G. Srinivasan of IIT Madras on rank order clustering. I'll give you an idea. This is not exactly how it is implemented, but I'll give you an idea as to the intuition behind the algorithm behind this. And I encourage many of the software engineers among you to actually try to implement this algorithm out of interest. So here, if you see the first square to the left, you have D1 through D8, right? All I did was I sorted it in the second step, where I'm assuming that each row is like a binary number. So if you see D5 comes as the first and D2 comes as the second. They're actually identical. It could have been D2 and D5, but for all practical purposes, I mean, it doesn't matter. But basically, we have sorted based on the row value. Then you transpose the matrix. And after transposing the matrix, you repeat the same for sorting based on the column value, right? So now you see this 11C7 has gone all the way up to the top along with C1, right? And then you repeat this process again. You can transpose repeatedly until there are no changes in the matrix. So, you know, this funny line over here is that you do it multiple times until there are no changes in the matrix. And then you count the number of digits, the number of ones in them, and then sort by the number of ones. I mean, sort by the number of ones in each row. You sort the rows by the number of ones in each row. And then you transpose again repeat. And eventually you will get clusters like this. The large clusters you will get on the top left. And you see, it looks like a beautiful block diagonal matrix, right? And you can invent these techniques. You can try these techniques out. You can read a lot about them. But essentially, what Abhishek did was groundbreaking. We found so many drivers working with customers in niche places. And Abhishek went a step further. He was like, why do people do this? And he spotted one case where a few drivers would make the same trip with the same customers. And they were kind of small shop owners who would share the spoils with the driver on the incentive given by the platform. Basically, the incentive was more than the burn of the petrol, the diesel cost. And you know, they would share the spoils. Another very interesting thing that happened was Abhishek spotted that there were a bunch of drivers, 8 drivers, who were driving around the outskirts of Bangalore, where you wouldn't expect actually any bookings, and they were booking each other, and they were having a fun time, right? So this kind of bi-clustering solution exposed all kinds of frauds. GPS fraud was exposed, you know, bad SIM cards, fake SIM cards that don't match the LUNS algorithm for the SIM ID, I believe, the device ID also. And all sorts of frauds were caught. And the hacked version of the customer app was also detected, because that's how a lot of these clusters were working. And we shut down website bookings because there was no GPS involved in website bookings at that time. And we noticed a lot of fraud happen this way as well. So net, a very cute solution, a little mathematical, but you just see how you take something as practical as this matrix and superimpose it in a supply-demand scenario, and you get these wonderful clusters. Quite shocking it was for a lot of people, and hats off. In my opinion, this is perhaps the most beautiful data science use case I've seen in my career. Perhaps the number one, I would think. And here are the resources on R. Abhishek had implemented it using R. You can find resources on Python as well. do a quick time check, taken 11 minutes. So I will move on to the third use case and basically e-commerce policy and alerts. I'll give you a little bit of a background. Unlike the Western world, India and a few countries, and many of you are from Nigeria and Kenya listening to this talk, maybe down the line, and maybe as well as the GCC and the MENA region. Cash on delivery was started in India, and it's unlike the Western world in the US, where you would pay using a Visa card or whatever, your MasterCard, you would pay on Amazon.com, and then you would prepay basically, and then the item would reach your doorstep. There is a fundamental difference in economies like India, at least at that time, but it's still quite prevalent that a lot of people are not tech savvy. A lot of people do not trust the courier and the delivery companies, and following up with the e-commerce platform for something that you prepaid for and haven't received is quite a nightmare. It just goes on in circles. So people are very defensive in not using technology if they're not, confident enough about the delivery system. So there was a big problem. There's cash on delivery is high, but the flip side of cash on delivery creates this a possibility of abuse and frivolous purchases called RTO, return to origin. In return to origin, basically what happens is that it's not a return. Say I'm a customer and you are an e-commerce platform. I place an order and it's on cash on delivery. The item is shipped, but then I either don't exist or I refuse the item, or I was just playing around with the e-commerce site. And then, I just wanted to, I was just a prankster and I just did that. Whatever the reasons be, the RTO costs the company round trip costs, right? So companies have to put up, if it takes say $5 to take from to ship the item, you've got to bring back the item again for $5, and there's a chance of breakage. And then you will also have to store it in a warehouse, which includes warehouse costs. So every e-commerce platform tries to set policy on how to stop this RTO of a user and minimize the number of returns. And the user's identification here is as simple as an email address or a phone number. So that's the assumption moving forward. So policy setting via statistical modeling. Let's talk about binomial distribution. And it's the most natural distribution to stop, or at least portray, the user abuse. If the average RTO, return to origin, across India or your country was P, and a user with N orders and R RTOs and returns from history, should we allow cash on delivery? COD is cash on delivery. Should we allow cash on delivery for the next N+1 order? We could use p-value and use a threshold of 0.05 from statistical testing, or 0.95 for cumulative right tail, and use this p-value NCR times p to the power r times 1 minus p to the power n minus r. And don't get intimidated if this formula is in your face and intimidating. Go watch some YouTube videos, read some books, and really understand what this is. And it's so simple if you explain it to yourself with a coin toss example. So there were a lot of people trying to come up with solutions. There were product managers sitting in a room. What should we do if 7 items have been ordered and 3 have been returned? So 7 and 3, which would be right here, it's 0.15. Should we allow the 8th order to be cash on delivery or not? Now, by simply using binomial distribution, and if you can see this formula here, I basically did this formula because I wanted to convert everything to the right tail, if you know what I mean. So instead of having a bell curve like this, I wanted the curve to be something like this, so that only the right side would be the problem, and this 0.15 would have otherwise been maybe 0.85 on the other side. So I wanted to convert that. So that's why I created a 1 minus binomial distribution. But basically, given an expected probability of 0.23, that is 23% of my total orders are RTO, are return to origin. Here's a customer who has placed N orders, N could be any number from say 2 to 23, and has done so many RTOs. Now, clearly the red region here is you block the cash and delivery completely. The yellow region is like, maybe you want to allow it. And if you want to allow it, you want to give that caveat that you probably want to tell the customer that, hey, you've done quite a few RTOs. Do you really, really want to buy this item? So maybe a second verification. But basically, based on the user profile and this lookup table, you could make a policy decision. And this lookup table was made using binomial distribution. Now, there may be days where you on sale days you may want to keep, you may accept higher RTO percentages, but on non-sale day you may want to change that 0.23, which is here, to 0.18 over here. The second, just below B, here is 0.23. And if you notice that the policy changes, so let's take an example. 10 and 4 is 0, 10 and 5 is 0.04, and 10 and 5 is 0.02. So the numbers change, and some the red zone changes if you change the expected probability. So this could be used for policy setting. So just like RTO, there's also returns, and there are customers who abuse returns left, right, and center. What you could do is you could take an average of RTO and average of returns and say here is 17%, and then make your policy. This is one way of doing it. Another way of doing it is assuming RTO and returns are independent. You may want to use an ellipsoid kind of a mechanism where you put the scores, the binomial scores for returns and RTO, and then and have different thresholds like 0.93 and 0.97. It'll become an ellipsoid, and then that way you can stop cash and delivery for them. Another, being creative with statistics, mathematics, and data. Again, ellipsoid is nothing but a circle with two radius, different radius on the x-axis and different on the y-axis. But again, don't get flustered. You'll realize this once you see it at your own pace, and you'll understand this a little better. So benefits of binomial distribution policy. It can be set to categories as well. For example, fashion and clothing, and if anyone here is familiar with this company called Myntra in India, their RTO percentages are significantly different from, say, an Amazon or Flipkart. And the reason is this, because the RTO for clothing and fashion is significantly higher, because people like to try stuff out before they say, no, we don't want it. Same with returns as well. So you can have a different threshold for the categories that have high RTO, like fashion and clothing. And you can have one for the others. It can be used as a reference for discussions. I mean, again, nothing is in stone. Data science is an art, and it's a collective art. So there may be more than one opinions, and you need to take those into account and agree that this is what we will do, and revisit it if it's not working out, right? It's a natural process. Binomial distribution is a natural process, and it's really simple. So you could set policy, and a simple example of using binomial distribution to set policy. I'll move on to the next statistical technique, which was, we spoke about it, we implemented quite a bit of it, and it was quite compelling. So 100 to 200 pin codes have got about 19,000, out of 19,000, constitute about 80% of your orders in the e-commerce. It's kind of like the Pareto principle, right? 80-20 rule, but again, it's much more skewed than 80-20. Now, how to find a pin code of the remaining that is unexpectedly spiking? So define unexpectedly spiking to yourself, right? And if you try to democratize this, even in this audience, you would have many opinions, and people feel strongly about their opinions, which is fine, which is good. But then here's a perspective using Poisson's process. Spiking orders from a pin code need immediate attention, to ensure that there is no mass abuse that is happening from that pin code. I'll give you an example that we noticed that a lot of the delivery companies, last mile delivery companies, which were located in not very popular pin codes, they tended to have a lot of, not a lot of genuine orders. So the delivery boy, out of fear that he would lose his job because that center may be shut down, would make bogus orders to e-commerce companies and make it suddenly, and then you would see a spike, right? So it's important to catch these kind of spikes. Alerting pin codes using Poisson's process. I'm not going to, don't get scared about this formula. Trust me, don't get scared. I know it is kind of daunting, but you can measure the order velocity of the expected order velocity and detect spikes based on an expected order. You can detect spikes based on an expected order. So one way is you could choose 1 day as your time period for each segment, and compute the mean number of delivered orders in the last 2 months. And then your time period is 1 day at a time. So here in this formula, lambda is your expected rate. T is the time period. In this case, we're going to use 1 day. So the T would be 1. And X is how many actual values did you see. What this tells you, this probability using this Poisson process, is that, is this awkward? Is this rare? Is this a spike, right? So there is a natural distribution that can be used to catch spikes. And you can do it across pin codes. You can do pin code cross category for a particular seller, because you need to do seller protection. We've seen cases where one seller had a disgruntled employee who left that seller and went and made a bunch of bogus orders, and which were all returned or RTO'd, right? Which are all cash on delivery. And they all, so, if a seller sells 10 items of whatever he or she has in a day, what's the likelihood of getting 15 orders or 20 orders, right? So that you can't go by simple ratios and percentages. You have to use natural distributions like Poisson in this case. So risky segments tending to have more than 15% RTO is also one thing that that we notice, that anything that's risky, that's dormant most of the time, comes up suddenly. It tends to be risky, and it contributes a lot towards the returns and the RTO. This is an example from the book, Michael Sullivan. I won't go through this in detail. I've kept this deliberately for students to, listeners to read this. This one example gave me an idea, and just because I read this example like 4 years before I actually implemented, or 5 years before I actually implemented the solution, this McDonald's manager problem came to my mind. I was like, why can I not take that problem and put it in the pin code scenario? And, you replace the values. And this book, by the way, Michael Sullivan III's Informed Decisions with Statistics, there's a link here, is probably one of the, is probably a book I would always keep, right? It's like I carry with me literally everywhere I go. The beautiful book, great textbook to, if you're teaching statistics, great textbook to have. If you're a student of statistics, great textbook to study from and use as reference. So you replace the formula, replace the values in the formula of Poisson process. And what happens is, basically, if you look at the first example, exactly 6 cars arrive between 12 noon and 12:05 with an expected of 2 cars per minute. So in this 5 minutes, you would expected 10 cars with highest probability. What's the probability that exactly 6 cars arrive? And you replace it and you get On about 6 of every 100 days, exactly 6 cars will arrive between 12 noon and 12:05, right? Our expected value would have been 10 because that's the most likely value in the range of values at a rate of 2 cars per minute. So yeah, I'll leave these, this is directly taken from the book, beautiful book, strongly recommend it. Understand Poisson's process, don't get flustered with the formula. And it is super useful if you can take something from a textbook and apply it in your practical life. In this example, I've kind of used Poisson's processes. It's a made up example, but basically there is a normal distribution equivalent of Poisson process for lambda, that's arrival rate greater than 15. But for everything arrival rate less than 15, better to use the Poisson process, Poisson's original formula. And then if we know most of the pin codes have less than 3 orders a day, right? Most, when I say most, I mean the long tail of the 19,000. We can use Poisson's process to identify spikes in pin codes that can be used in call for action. The call for action could be the verification team, order verification team, quickly getting in and inspecting the orders, eyeballing them to say that something is happening, or maybe these look genuine, maybe these don't look genuine. All of that. So you can send the operations team all the orders for the pin codes that are seeing unexpected spike to see if they're safe. And you could perhaps even stop cash on delivery automatically for orders that are suddenly spiking in a particular pin code. And these are for the long tail, right? The 18,800 pin codes that order rarely. So if you look at the time series, you see 1 order on day 1, 2 orders on day 2, 2 orders on day 3, 1 order on day 4, and so on. And suddenly 9 orders on whatever the 9th day, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9th day. Now, if I take a 3-day moving average as my lambda, so I get 2, of course, I've rounded it up, 1, 2, 2, 3, so on and so on. Now, if my lambda is 3 and the new value that I get is 9, is there a spike? And Poisson process says, yes, there is. For time period t equal to 1, for lambda equal to 3, you can see clearly there is a spike. So statistics will match your intuition. Even if you crowdsource and ask a bunch of people, do you think this last point is a spike? And you can vary it and ask different people at different times. Most times you will be right. So statistics, fundamental stats is a match to intuition. That's definitely a take back that I would like you to take. So you can use statistics for policy like this. A quick check on time. We have only 12 minutes and I have 3 huge use cases. Question to Raksha, can we, this could well go over the stipulated 1 hour. All right, so I'll try to zip through this shipping address correctness as well. And here is a project, right? Again, this was not completely implemented, but I'm asking questions to the audience on how would you go about solving this problem, right? So most addresses in the world have a zip code or pin code, at least that I know of. But in some form, there's a zip code and pin code. And the zip code and pin code is used for shipment of a parcel before its journey to the last mile. So from the warehouse or from the seller all the way to the last mile, there is a pin code or zip code involved. Some people make mistakes, whereas some addresses are deliberately entered wrong, especially for COD. And I've tried this myself. Top e-commerce companies across the world, I've spoofed addresses, I've written wrong pin codes, and they make the order for COD wherever COD is applicable. So this won't work in the United States, or maybe won't work in the UK or Europe. But wherever COD is present, I can go and write rubbish addresses, or I may make a mistake in my address. Now, one question for the audience is, given the words of an address, can you check if the pin code entered is right? So you predict a pin code using a model based on the words, And does the predicted value equal to the entered value? That's one way of looking at things. It's nice, but yes, you'll find, Mahatma Gandhi Road. Mahatma Gandhi is father of the nation for India. You'll find it across many cities, and in each of your countries you would have maybe Martin Luther King Road or something like that. That's really common. So the prediction of the pin code may not be very accurate. However, if you pose the problem the other way around, is that given a pin code, do the words in the token, the words or the tokens of the address, match the frequent words in the pin code? Now, again, this is not an ideal data science way of solving things, but at least it is a check and balance. It's a fundamental starting process, if you have nothing in place, to check whether the words entered in the pin code are actually belong to the pin code based on historical data that you've accumulated. I'll give you an example, and I come from Mumbai, and the zip code that my parents live in is 400093. And one small mistake of 400092, you see it's almost like quite a few kilometers, 21 kilometers, 40 kilometers, 38 kilometers, it says here, 38 kilometers away. Now, if this looks like a perfectly genuine address, but the pin code was wrongly entered, now what happens as a result of this is this item has to be shipped again by the e-commerce company to the 400093 address, and then it'll reach the destination. This obviously is the kind of errors that cost e-commerce companies quite a bit, and there's a lot of back and forth, a lot of communication between the delivery company, the logistics company, and the e-commerce company. So simple checks and balances could have corrected this. Hey, we don't find words of, is your pin code right or is your address right? Right? I mean, immediately posting that question at the time of the order would help. Stitch in time saves 9, would save a lot of costs. Text analysis, I'll try to speed through this. You need to remove stop words like nagar. We consider each pin code as a document and consisting a bag of words of tokens from the addresses where the order was successfully delivered historically. And then you remove some stop words like road, street, nagar, and so on. Apply TF-IDF on the matrix. So what TF-IDF does is it exaggerates the frequent words that are occurring in not all but fewer documents, and reduces the noise in the matrix. So you can apply TF-IDF and create a word vector for each pin code, and then you can apply, as mentioned earlier, the green this green part where at least is the incoming order, does it match to my expectations to the pin code? So this is something you can do. There are small cities or well-planned cities in India. At least you have Gurgaon or Chandigarh, Greater Noida, which have, like New York City, they have streets and avenues kind of perfect grid-like. So you could perhaps pre-map these cities to really make sure that orders from these cities are correct. So it requires some work upfront. And from past experience, well-planned cities tend to have very short addresses. So maybe you can ask for more details like, hey, sector number, apartment name, any landmark nearby. You can pop questions to the person placing the order one after the other to make sure that they enter the right kind of data. And then another problem that you would see is, here, I've seen this really Indian Army cantonment. He really meant Indian Army cantonment, but he did not put any spaces in between. And then again, Sarjapura Road, he just put, he conjoined the words. So there's a huge opportunity for algorithms to be built and also build good dictionaries, named entity recognition. What is a road name? What is the apartment name? And so on. So for students, working on this, if students who want to do some projects, for the college graduation or course graduation, I strongly recommend that you actually try these things if you can, and it would be of huge value. Like in India, you have something known as Map My India, which kind of does a lot of this. For countries like Nigeria or Kenya, maybe you're the ones who are going to create Map My Kenya or Map My Nigeria. So there is a whole opportunity, a huge opportunity for fundamental techniques to be used, data science techniques like named entity recognition, to come up with extraction of features from the address. Quick check of time. We have 5 minutes on the schedule thing. I'll try to make this quick. But this one is so cute. And this gibberish monkey addresses is so cute. I'll tell you a little bit of a background story here. I was walking down the steps going for lunch, and the product manager was walking back up. The elevator was not working. And excuse me, he asked me, hey, Vijay, there seems to be a problem, man. I mean, we get all these addresses that are total gibberish, like, real crap addresses. Can we do something? Can we find them out automatically? So I took some time. I went and did some Google search. And before I get further into details, right? You see the first one, it does not look gibberish. The second one certainly looks gibberish. New Delhi, not gibberish. 1 bar, 2 bar, 65 bar 8, perhaps gibberish. I don't know, maybe, contentious, but house number 433 does not look gibberish. So how do we isolate these? So in statistics, there is, in probability theory, actually, there is something known as Markov model, which is a stochastic model. And the definitions and names could get quite overwhelming for students here, but you can double click on each of these to understand the abstract meaning of them. But here is a practical example. Or the simplest example is a simple Markov model is the Markov chain, which basically says your next state depends only on your previous state and not before that, right? So how can you use Markov model and gibberish addresses? Where's the connect? I did a Google search, and I have to give credit to this person, Renaud. He had explained this and done this. If you search Google, search for gibberish detector in Google, you'll probably get this link. But basically, the 2-character Markov chain is something like this. Given an A, and if you have a lot of addresses or a lot of words, given an A, what's the likelihood you'll see another A? Quite small, 0.001. What's the likelihood you will see a B? It is, yes, there was a question. Okay, so we'll get to the questions at the end. We'll try to finish the material first. So yes, given a character, what is the likelihood of other characters, right? The likelihood of a Q is actually really small. The likelihood of A, quite small. B, not as small. Z, yeah, it's quite small. So that's basically the concept of Markov model with this gibberish detector, where is it common to see a Q followed by a T in an English word? No. Is it common to see a Z followed by an S in an English word? No. Is it common to find 2 consecutive A's in an English word? No. Now consider these 3 words here. You have BFA. How often would a genuine English word have a B followed by an F? Unless it's an acronym, absolutely 0, right? Same way for, what about for lab, bad, and fig? These look genuine. So Markov model introduction in this case is by chaining probabilities based on earlier knowledge, we can get a probability of occurrence of any word from a given dictionary, right? So we can build a dictionary, like assuming a prior information of these probabilities is already built, right? So probability that the first character is B times probability that the second character, the next character is F given the prior character B times probability that the next character is F, is A given F. So you kind of chain the probabilities and you can form some sort of a way of comparison between them, between the words, the possibilities between them. Now, if you take a 500,000 English words, or if you take addresses from India, you can pretty much say that the first character probability should be dropped. It's large enough, or you can assume equal distribution and then drop the first character altogether and just chain the Markov part of it one after the other. And that's what you would do for simplicity's sake, and it's for comparison's sake. You would do that. And what you get is, I made up a lookup table of some 56,000 addresses in India of delivered orders. I took space as one possible character, A to Z and A to Z, and just count how many times do these occur. So in this case, there were when A was the first character, only 3 million times, and only 11,000 times A was the second character. So, stuff like this. You build this up completely. And if you use this as a lookup, BFA gets a very, very small score, 0.000093, whereas LAB gets a bigger value of 0.0035. So obviously you've got a way to say the lab is a better word, a non-gibberish word compared to BFA, right? So at least you got a comparator going. The problem now is when you have a 3-letter word and a 4-letter word. Now, GLL clearly is gibberish, but GLAD is an absolutely perfect English word. Now, how do you score GLAD over GLL? In this example, as you're multiplying probabilities, the numbers keep getting smaller and smaller. And GLAD has, 1, 2, 3 consecutive. So GL, LAAD, whereas GLL has only GL and LL. So obviously, GLAD is going to have a smaller score, but hey, wasn't this supposed to work in the first place? Why is GLL getting a better score? And the answer to that is logarithm. You've got to understand the power of logarithm in data science. Basically, a very common technique used is log averages, so averages of logs, as against using the chained probabilities as is. One reason in the chained probability case is that you could get an underflow error if you have a long word like, hyperbole. If you had that word, you would have so many small numbers multiplied with each other that your computer would give you an underflow error. The other reason is because of the property of log. Log converts addition to multiplication, right? And an average taken on numbers is, well, how do I put it this way? If you take a log average and divide by the number of, 2 characters at a time, you would get comparable numbers for your comparison. So let's look at this in this case. If we had your denominator is 2 because GL and LL, and here your denominator is 3, GL, LAAD. So you have denominator of 3. Now, if you take the logs, it converts multiplication into addition, and you can take the average and minus 2.77 is a better number that is definitely larger than minus 3.15. So lower the log average based on 2-character Markov chain seems to give better results. Or is it? Let's check. Actually, it does. And as it happens, you can create the entire table. You can store the probability, and you can also store the log probability and make this a simple lookup table of 27 by 27, store it in cache. And you can check for gibberishness of addresses. As I mentioned before that, I found the gibberish detector on the net that included log, but then I had to apply my spin where I had 50,000 addresses, and I used the left tail to basically put a 2 sigma rule on the bell curve that I got with all the scores of addresses. And indeed, the ones below the 2 sigma or below looked absolute gibberish. And this was catching about 300 to 500 orders a day. And people were really happy that we were able to catch gibberish addresses in e-commerce. The pros and cons, sweet and simple, does fairly well in practical cases, computationally very efficient and very lightweight. The cons are that it does not completely take care of all use cases. So it can be bypassed. And I cooked up this example, Tati Te, Papi Pope. I just made up an example where your gibberish detector would not actually work. But that's all right. I mean, not everything works all the time. And at least you have your defense mechanism put in place for your e-commerce website. This is, I believe, the last use case. Quick time check, not too bad. Catching bulk buyers in real time, in near real time. Now, most of the fundamental analytics is based on equality. So for example, joins in SQL and database indexes use comparator method. Given that two objects are comparable, are they equal or are they not equal? And can you make a total ordering? But catching fraud requires clustering based not just on equality, but based on similarity. And what is the definition of similarity and how does it differ from equality? Basically, in this case, let's kind of roll back in time, and it's kind of similar to congruent triangles are also similar, but not that similar triangles are always congruent. So it's kind of something like that if two things are equal, they're definitely similar, but two things could be similar, but not equal, right? So that's the rough definition of similarity. And just like you have similarity, you also have distances. And what you say is they are essentially the reciprocal or one minus of each other, depending on which similarity topic you've taken. There's cosine similarity, there's edit similarity, there's Jacquard similarity. There's quite a few types of similarity, Euclidean similarity. So more similar two objects are, lesser is the distance between them and vice versa. So that's the definition, rough definition of similarity and or relationship between similarity and distance. So let's take two cases, right? Two examples, addresses A1 and A2. Mega Das Colony, Maratha Halli, near flyover, Bengaluru. And here in the second one, A2 is Mega Space Das, complex and not colony, Maratha Halli, near bridge, not flyover, Bengaluru. And again, it's a cooked up example, but it's very well could be an example in real life that comes about like this. So we can ignore the city and pin code because they're basically the same, but given a pin code, don't these addresses look in the same area? They actually do. Someone called it a complex, someone called it a colony, and someone called a bridge a flyover, somebody called a flyover a bridge. So the first thing that comes to mind is, how do I measure the similarity between them? And the most common thing used by a lot of the engineers who study for Google interview or a FANG interview is this very popular technique called longest common subsequence. It basically uses a recursive technique, and it's O of n square in the size of n square is a complexity in computer science. It's O of n square in the complexity of the length of the strings. And basically, as you can see here, the LCS of A1 and A2 is 34. That much is a commonality between these two strings. This is the recursive formula for LCS. I won't get into it, but there are plenty of YouTube videos and enough stuff on the internet. But it's really cute, and if you understand longest common subsequence, then you've understood one of the basic problems in dynamic programming, or one of the big problems that dynamic programming solves, which is an algorithm design technique that is dynamic programming. So the definition of edit distance is length of string 1 plus length of string 2 minus twice the length of the LCS. So this could be my definition. You could have your own definition. Note in text, there's no mention of edit similarity, but you could define your own. I mean, you could define one as LCS divided by length 1 plus L2 minus 2 times LCS of the two strings. And just like edit similarity and edit distance, you have something called Jacquard similarity and Jacquard distance. It basically is very simple. It takes the union and it takes the intersection, which is in green, divided by the union, which is a blue, green, and red, and defines what is Jacquard similarity. Here, or Jacquard distance. Here as well, you could be creative and come up with some more definitions where you could say intersection only over set B, or intersection only over set R, or intersection over union of B and R. So you can come up with your own measures and be creative. And I've done this in the past and it works out really well with Jacquard similarity. So we use Jacquard similarity to find similar addresses. And why we preferred Jacquard over longest common subsequence was because people deliberately mistype addresses and rearrange words in the address. This we've seen in India quite a bit. Now, one way around is you could order the tokens by alphabetically, that is alphanumerically, and then apply LCS. But LCS is an O of n square algorithm, whereas this Jacquard similarity one was extremely fast. And we were looking at clusters of addresses. And I define this term called bimilligrams. So I take addresses, the tokens of address A1 and A2, and I put, I find them out and have a 2 by 2, or I have a vector of 26 square for the English alphabet. And I put a 1 if ME has occurred. So I find M and the E after that, and I put a 1. So I create a bit vector. And once I create a bit vector for A1 and a bit vector for A2, all I have to do is a logical AND for intersection, or a logical OR for union, and I can get the Jacquard similarity. And I keep a Jacquard threshold, and I'm able to find similar addresses. In the interest of time, I'm going to make this really short. Basically, we didn't want to compare addresses in Mumbai and Delhi. It didn't make any sense. So we use pin code as one of our points of partitioning. The next thing we use is a 24-hour gap for clustering of addresses. And we kept also the same item, the same SKU being bought. And this gave pretty good results. I'll jump the slides and go directly to the example. In one sample data that we found, you can look at the addresses here. Mansa Tala Lane, Monsha Tala, all kinds of very interesting names for the same address. And they were buying pretty much they all clustered in the same ID. And they were all buying Micromax Canvas Spark 2 Plus. And this cluster size was 15, and they were all cash on delivery in the same pin code. Now, this was a revelation. I mean, we got huge accolades for this. And a lot of companies, a lot of co-workers were like, had jaws dropped when they saw that we were clustering this kind, and we had prevented a lot of fraud that was happening. And, just as if you're interested in e-commerce and you wanted to put each of these solutions in order, I'd put the gibberish address detector first, followed by incorrect pin code, followed by a binomial distribution violation of the actual customer, and then spiking of the Poisson process. So I'd put these two in some order so that you could say that this order needs attention of some sort. And for bulk buy, you could create a separate dashboard for your operations team, and they can review and act on it. They can either cancel all these orders, or they can call them up and re-verify, or decide to ship it. The one thing that I should mention is there is something known as single linkage clustering, which I should have taken time to explain. But basically, what is single linkage clustering? If A is similar to B and C, even if B and C are not similar based on a threshold, I can cluster A, B, C together. And now let's say I have a cluster A, B, C, and I have another cluster D, E, F. And a new coming order G is similar to D in this cluster, and is similar to C in this cluster. then you should merge both clusters because G has brought the linkage of, clustering altogether. So the single linkage clustering was used for clustering addresses after using similarity. And we found remarkable results for a lot of the customers in our, a lot of the use cases for bulk buy. So with that, I will end with my resources. Numbers Rule Your World by Kaiser Fung, a definite read. I've read this book twice. It opens your mind to statistics. So if you're a manager or if you are someone who's seasoned and senior, this book will kind of open your eyes to how things are done. Creating a Data-Driven Organization by Carl Anderson, another phenomenal book, very cute read. Of course, the statistics book that I have used of Michael Sullivan, and then videos like rank order clustering. And there is this course by Stanford. It's a free course. It's by Professor Jeffrey Ullman, Professor Anand Rajaraman, and Professor Joel Leskovec. Brilliant video. I think this one video was my turning point into data science and big data and data science. Definitely something that you should take. So with that, lastly, I'd like to say that if you have any questions, you can reach me on LinkedIn. You can reach DataHour if you want a deep dive in any of those use cases mentioned. If you want a solution implemented, you can reach out to Chinmay at PySquare.io because I licensed out a lot of the algorithm implementations to him, and he runs it. He implements it for various customers on demand. And then the next DataHour session by me, I would go through another bunch of use cases, Dhobiwala.com, e-commerce RTO, DriveU. I was the oldest participant in Swiggy's data hackathon. And then my recent foray with population healthcare analytics. I will be focusing on data mining and strongly recommend that you throw away your beer and diapers example because it's way more powerful. I'll be talking about actionable insights, frequent item sets on large data sets using Theta Sketch, and then automation with data on small little use case. So with that, I have taken 18 minutes over. Sorry about that. I'll try to be on time moving forward, and I'm open to Q&A. First question, as for taxi fraud, how did you handle false positives? Good question. So, when you are reviewing somebody who's potentially false, you call them to a taxi driver who's fraudulent. They have to be some sort of statistical outlier, or they have partaken in some connivance or something of the sort. You call them over, you make them talk to the operations team. And typically in the operations team, you decide whether you have to take action against the person or not, or you ban the person, or you fine the person, or give a last warning. So that's basically how it works. So it's more recall biased than precision biased, if you may. And that's typically going to be the case with anything that's unsupervised learning. So that's the answer. I hope that answers your question, Rogers. Second question, in terms of comparison of trip numbers, would it be good to also factor the distances traveled? Absolutely. Absolutely. You should have an entire profile for a driver, number of trips, number of the total distance traveled, number of hours worked in a given day, and maybe also, do a distance over time split for each trip to see the average speed of the driver and if it's over the limit. So yes, you have to be creative. So yeah, that's definitely a +1 there. Next one, Mayank Gupta asks, most of the pin codes must be of metro cities. That's not quite true. If you look at, if you do a Google search, you will find there are 19,000 plus pin codes. In fact, as we speak, one of my good friends is running a trucking company, and he does pin code based matching of demand and supply. And yeah, there are 19,000 pin codes across India. In fact, even Mizoram has got 797001, I believe. So I hope that answers your question. But well-planned cities in India are very few. That's true, and they're growing. But if you put your effort up front to understand what the structure of the addresses look like in well-planned cities, then your verification process is much faster, and you won't apply what applies to other parts of India to well-planned cities. Next one, how did you handle words that are not English in nature while developing? Okay, so Rogers, I basically was doing the addresses in India. So one example, HDFC is a very popular bank in India. When, HDFC is not a common English word. So I had to retrain the word HDFC so that it did not become gibberish with respect to India. Now, if you're looking at addresses in Poland, for example, in Poland, in the English language, you won't find very often words which have 4 consonants, right? Non-vowels. But in Poland, you would find 4 consecutive or 5 consecutive letters which are consonants. So you have to train your model based on not having English in nature. I mean, if you're from Nigeria or from Kenya, you have to train it based on your addresses or your names that you have. What works for India may not work for Nigeria. So you'll have to build your own model for Nigeria or Kenya. If the country, next question is Mayan Gupta, if the country is something like Hindi-English mix, the aptness of such a solution would be in question. I don't know what this is about. Is it about gibberish, Mayank? If you could come back. Santan Chakraborty, I think you have to learn math. I think, and honestly speaking, right, even there are data science jobs that I don't qualify for, right? I don't have a PhD in electrical engineering or physics or computer science, though I can understand a lot of the theory. If you want to be a pure computer scientist, I would strongly recommend that you find a way to get a PhD. You can't just take a course and be a popular data scientist, I would say. Next one, Shankar Sahu, which case we use prior distribution? There may be cases, I can't think of one, but basically I wanted, in the case of the gibberishness, I wanted to get rid of the first letter because I wanted to give equal probability. They could have skewed my results quite a bit. So I was being creative there. You can try something on your own. So another question from Shankar, suggest some unique project for data science that would help get a job. I would say be an inventor. Let the jobs come running to you. I mean, do a startup and get acquired, or provide a service that would be superb. I think this whole idea of running behind a job, while it's a reality, I think what I would strongly recommend, and I know I sound quite prophetic, or I sound very idealistic when I say this, but what you should be really doing is maybe try a few Kaggle competitions, try to win a few, and try to do something. So that's my suggestion. Looks like Markov model is based on conditional probability. Is it similar to naive Bayes? Or vaguely. Let me explain it this way. You would use Markov model when you have a string or a chain of things to do. You would use this conditional probability of like what naive Bayes is used at as when you have a predictive problem where, if it's sunny, then your likelihood of playing tennis is high. That kind of thing. So you're evaluating each one with the other. That's naive Bayes. So again, different, not the same. I wouldn't even call them the same, but you have to look at them separately. But yes, both of them have this idea of conditional probability. That's the only commonality, I would think. How do you select a technique for going for a solution? What should be the approach? Sometimes try it, right? Put your worst solution first. It takes experience. Then iteratively, you will come up with very interesting solutions. It's okay to be wrong. I was never right the first time. I'm still not right very often. So I enjoy the process, and I think that's what your learning should be. Try a cattle competition. It's okay if you don't understand anything of what's happening, but your persistence will make you understand. So, and yes, you need to equip yourself with fundamental mathematics. Understand basic log, understand basic calculus, understand fundamental statistics, understand what's a chi-square test, what's a Fisher test, t-test, all of those. And linear algebra is extremely important, I would say. So yeah, that is, I think we've done answering all the questions. Yeah, you could collect these questions on the webinar. I can answer it offline. But again, there are some really smart people, out there. Don't underestimate yourself. Try to learn with humility. And I think that's what will finally help you, go forward. Thank you so much. And it was fun explaining these.